Picture Scandinavia in the 8th century, cold, dark, harsh. A landscape of fjords slicing deep into mountainous coastlines, of forests so dense they seemed to swallow the light, of winters that lasted half the year and tested the survival of anyone foolish enough to call this place home. This was not a land of easy living. Agriculture was difficult, limited to narrow coastal strips and valley floors, where the soil was thin and the growing season painfully short. The sea was everywhere, dominating life, defining possibilities, and presenting both opportunity and mortal danger. The Norse people, the Vikings, were hemmed in by geography. Mountains blocked expansion inland. The bitter climate made large-scale farming nearly impossible. Population pressure mounted as communities grew. Young men faced grim prospects. Limited land meant limited inheritance. Younger sons, those without claims to family farms, had few options. Stay home and work someone else's land as a laborer, hope for a marriage that brought property, or starve slowly while watching older brothers inherit everything. But there was another option. The sea. That vast, terrifying, utterly unforgiving expanse of cold water that surrounded their homelands. For most of human history, the open ocean was a barrier, a boundary that marked the edge of the known world. Ships existed, certainly, but they hugged coastlines, crept carefully from harbor to harbor, and retreated quickly when storms threatened. The idea of sailing far from land, of crossing open ocean without sight of shore for days or even weeks, seemed like suicide. And then the Vikings built something different, not through sudden inspiration or divine intervention, but through generations of incremental improvement, trial and error, catastrophic failures, and hard-won knowledge passed from shipbuilder to shipbuilder, from sailor to sailor. They built a ship that could do what no other vessel of its time could manage: cross oceans, navigate shallow rivers, be pulled onto beaches without harbors, ride out storms that would shatter other ships, travel vast distances at speeds that astonished everyone who witnessed them. The Longship wasn't just a boat, it was a revolution in wood and iron, a technological breakthrough as significant as the stirrup, the printing press, or gunpowder. It transformed the Vikings from isolated Scandinavian farmers into the most feared and far-reaching maritime power Europe had ever seen. It enabled them to appear suddenly, seemingly out of nowhere, striking monasteries, towns, and trading posts, before vanishing back across the water faster than any army could respond. It allowed them to trade, to explore, to settle, and to conquer across distances that should have been impossible. But here's the thing that gets lost in the dramatic tales of raids and battles. The Longship wasn't built by warriors, it was built by craftsmen, by shipwrights who understood wood like a language, who could read the grain of a tree and know exactly how it would behave when shaped, bent, soaked, and subjected to the violent forces of wind and wave. It was built by communities that pooled resources, knowledge, and labor to create vessels that represented the absolute cutting edge of medieval technology. The Longship was a masterpiece of engineering born from necessity, refined through disaster, and perfected through obsession. Every plank, every nail, every curve and angle represented accumulated wisdom about how to survive and thrive in one of the harshest maritime environments on Earth. And tonight, we're going to understand exactly how they did it, how they took trees from the forest and transformed them into dragons that conquered the seas. This is the story of how Vikings built their famous longships. Not the romantic version, not the Hollywood version, the real version. Detailed, technical, obsessive, and absolutely fascinating. Because once you understand how these ships were made, once you see the incredible sophistication hidden in what looks like simple construction, you understand why the Viking Age happened at all. The Longship didn't just enable Viking expansion, it caused it. Without this ship, without this specific combination of design innovations and construction techniques, the Vikings would have remained exactly what they had been for centuries before. Farmers and fishermen clinging to the edges of a harsh northern world, unknown and irrelevant to the broader sweep of European history. The Longship changed everything, and it all started in the forests. Long before the first plank was shaped, long before the first nail was hammered, long before the shipbuilder even began sketching designs in his mind. The process of building a longship began with a walk through the forest, not a casual stroll, a careful, deliberate survey. The shipwright, often accompanied by the community's most experienced woodsman, would spend days or even weeks searching for the right trees. Because in Viking shipbuilding, not just any wood would do. The selection process was exacting, unforgiving, and absolutely critical to whether the finished ship would be seaworthy or a death trap. Oak. That was the gold standard, the undisputed king of Viking shipbuilding timber. Specifically, old-growth oak, trees that had grown slowly over centuries in the cold Scandinavian climate. Fast-grown oak, the kind you might find in warmer, more fertile regions, was too soft, too brittle, too prone to splitting under stress. Slow-grown oak, with its tight growth rings packed closely together, was dense, strong, flexible, and remarkably resistant to rot when constantly exposed to seawater. But not just any oak tree would work. The shipwright needed specific shapes, specific growth patterns. For the keel, the backbone of the entire ship, he needed an absolutely straight trunk, ideally 50 to 60 feet long, without significant branching or defects. Finding such a tree was rare. Most oaks, especially those growing in competitive forests, developed curves, knots, and irregular growth patterns as they competed for sunlight and space. For the ribs, the curved structural elements that gave the ship its shape, the shipwright looked for trees that had grown in particular ways. An oak growing on a hillside, bent by wind and gravity, might develop a natural curve perfect for a rib. A tree that had split into two main trunks early in life might yield two perfectly symmetrical, curved pieces. The shipwright learned to read trees like texts, understanding how decades or centuries of growth had shaped the wood's internal structure. And then there was grain direction. This mattered desperately. Wood is strong along the grain, but weak across it. A plank cut perpendicular to the grain would split easily, catastrophically, under the flexing and twisting forces that ships endured. Every piece had to be cut so that the grain ran in the direction of maximum stress. For planks running the length of the ship, the grain needed to run lengthwise. For curved pieces, the wood's natural growth pattern had to align with the curve, not fight against it. The Vikings understood something that even many modern woodworkers miss. You don't impose your design on the wood. You work with what the wood wants to do, what its structure naturally supports. Forcing wood to bend against its grain or cutting it in ways that violated its internal structure resulted in a weak, unreliable construction. But working with the grain, respecting the wood's natural properties, created joints and shapes of extraordinary strength. Finding the right trees could take months. Once identified, the trees were marked but not immediately cut. Timing mattered. The best time to fell oak for shipbuilding was late autumn or winter when the sap had retreated and the wood contained less moisture. Wet, sap-filled wood was heavier, harder to work, and more prone to warping and cracking as it dried. Winter-felled timber could be worked immediately or stored for years with minimal deterioration. The felling itself was an event, a community effort requiring careful planning and execution. These were massive trees, some over 100 feet tall and several feet in diameter at the base. Falling them required coordinated axe work by multiple men, careful notching to control the direction of fall, and experience to avoid shattering the trunk on impact. A poorly felled tree, one that landed badly or struck other trees on the way down, could be ruined. All that searching and planning wasted. Once felled, the real work began. The tree had to be processed on site because moving whole trunks through dense forest was nearly impossible. Using axes, wedges, and enormous amounts of labor, the shipwrights split the trunk longitudinally, following the grain. This wasn't sawing, which cuts across grain and weakens the wood. This was splitting, using wedges driven carefully along natural weak points in the wood's structure, separating it into sections that maintained grain integrity. A single large oak might be split into dozens of usable pieces. The straightest, clearest sections became planks for the hull. Pieces with natural curves became ribs or other shaped components. Even the branches weren't wasted. Smaller, curved branches could become supports, braces, or decorative elements. The Vikings used every part of the tree they could, because acquiring good timber was expensive, difficult, and time-consuming. Waste was unacceptable. The split sections were then shaped using axes, not saws. Viking shipwrights used remarkably sophisticated axes with different blade profiles for different tasks. Broad axes for rough shaping, narrow axes for detail work, side axes for smoothing surfaces. The skill required to shape timber accurately using only axes is almost incomprehensible to modern craftsmen used to power tools and precision saws. Yet Viking shipwrights could shape a plank to within millimeters of the desired thickness, creating smooth curves and precise joints entirely by eye and feel. After shaping, the timber needed seasoning, drying slowly to reduce moisture content without cracking or warping. Some pieces were used green, particularly those that needed to be bent. Green wood bends more easily than dry wood and can be shaped into curves that would crack dried timber. But structural pieces, especially the keel, needed to be dry to prevent the ship from distorting as the wood continued to dry after construction. Timber preparation could take years. A community planning to build a longship might spend several years accumulating the necessary timber, selecting trees, processing trunks, and storing planks as they seasoned. This preparation phase was invisible, unsung, and absolutely essential. By the time construction actually began, the hardest work, the work that determined whether the ship would be excellent or merely adequate, was already done. And the Vikings knew this. They didn't rush, they didn't cut corners. They understood that the sea was unforgiving, that a weak plank or a poorly chosen piece of timber could doom an entire crew. So they walked the forests, read the trees, waited for winter, felled carefully, split precisely, shaped obsessively, and only then, only after all this preparation, did they begin the process of actually building the ship. The relationship between Vikings and their forests was intimate, almost spiritual. The forest wasn't just a resource to be exploited. It was a living library of building materials. Each tree a potential component if only you understood how to read it, how to recognize its purpose. An experienced shipwright could walk through a forest and see, not trees, but ships waiting to be released from the wood. Different species served different purposes. Oak, as we've discussed, was supreme for structural elements. Its density and resistance to rot made it irreplaceable for the keel, planking, and major structural pieces. But pine had its place too. Lighter than oak, easier to work, pine was often used for masts, where height was needed, but weight had to be minimized. A tall oak mast would be incredibly strong, but so heavy it would affect the ship's stability. Pine offered a better balance, strong enough to handle the forces, but light enough not to destabilize the vessel. Ash, another common Scandinavian tree, was prized for oars. It combined flexibility with strength, bending slightly under the enormous forces generated by rowing without snapping or developing stress cracks. An ash oar could flex and spring back thousands of times over its lifetime, absorbing shock and distributing forces in ways that made rowing less exhausting and equipment failures less common. Spruce, particularly its roots, provided the lashing material that bound ribs to planking. Spruce roots could be dug up, cleaned, split, and soaked to create incredibly strong, flexible cordage. Unlike rope, which could rot or fray, spruce root lashing maintained its strength year after year, allowing the ship to flex and move without the rigid connections failing. Even the smaller trees and bushes had roles. Willow branches, flexible and easy to weave, might be used for fenders, protective coverings that prevented hulls from being damaged when ships came alongside each other or docked at rough stone quays. Birch bark, thin and waterproof, could be used as gaskets and seals in various applications. The Vikings lived in what we might call a wooden world. Everything they built, used, or needed came directly or indirectly from the forest. Their homes were wooden, their tools had wooden handles, their furniture was wooden, their carts, sleds, and skis were wooden. They ate from wooden bowls with wooden spoons. They drank from wooden cups. They lit their homes with torches made from resinous pine wood. And of course, their ships, the technology that defined their civilization, were wooden. This deep relationship with wood created a culture of sophisticated material knowledge. A Viking craftsman didn't just know wood as a generic material. He knew specific woods, specific growth patterns, specific properties that could be exploited for specific purposes. He knew that oak from a north-facing slope grew differently than oak from a valley floor. He knew that a tree stressed by constant wind developed compression wood on one side that was denser and stronger. He knew that a tree growing near water might have subtle differences in grain structure compared to one growing on dry ground. This knowledge was empirical, built through observation and experience rather than theoretical understanding. The Vikings didn't know about cellulose structure or lignin bonds. They couldn't explain scientifically why splitting wood along the grain created stronger planks than sawing, but they knew it was true because they'd seen the evidence. Planks that were sawn across grain failed. Planks that were split along grain survived. Simple, empirical, undeniable. The accumulation of this knowledge took generations. A craftsman in the 8th century building ships was working with knowledge accumulated over hundreds of years by his predecessors. Each generation added to the understanding, refining techniques, discovering new applications, finding better solutions to persistent problems. And critically, each generation passed this knowledge forward, teaching apprentices not just what to do, but why, building understanding rather than just memorizing procedures. The forest walks, then, were more than timber selection. They were teaching opportunities. A master shipwright bringing his apprentice into the forest wasn't just showing him which trees to mark. He was teaching him to see the way a shipwright sees, to recognize the subtle signs that distinguished excellent timber from merely adequate timber. He was teaching him to think about the ship as a whole, to understand that every piece needed to work with every other piece, that selecting timber for one part of the ship affected possibilities for other parts. An apprentice learned to ask questions. Why do we want this curve for a rib? Because it matches the whole shape we're planning and uses the tree's natural growth pattern instead of forcing wood to bend unnaturally. Why do we reject that straight oak? Because look at the bark. See those patterns? They indicate internal rot that will weaken the wood even though the outside looks fine. Why do we mark trees now but wait until winter to fell them? Because we need time to organize the work crew, prepare the tools, and ensure we fell during the optimal season when sap is down. This patient, thorough education created craftsmen who didn't just follow procedures. They understood principles, and that understanding allowed innovation. When a craftsman truly understood why certain techniques worked, he could adapt them, improve them, or invent new approaches when circumstances demanded it. The forests themselves were often managed, though not in the modern sense of industrial forestry. Communities understood that overrunning would eventually exhaust their timber supply, so trees were harvested selectively with an eye toward sustainability. When a large oak was felled for shipbuilding, younger oaks were left to mature, ensuring future generations would have timber for their ships. This wasn't environmental consciousness in the modern sense. It was practical self-interest. A community that cut all its trees would eventually have no ships, and without ships, they couldn't fish, trade, or raid. The forest's preservation was their survival. Some forests were even semi-sacred, protected not by law, but by tradition and community consensus. The best stands of oak, those that consistently produced superior shipbuilding timber, were jealously guarded. Outsiders might be prevented from cutting trees there. Even within the community, access might be controlled, requiring permission from a chief or consensus from community leaders before any tree could be marked. This created an interesting dynamic. The forest was simultaneously resource, treasure, and legacy. It provided the materials that made Viking expansion possible. It represented wealth because good timber could be traded or used to build valuable ships. And it represented obligation to future generations because responsible management today ensured children and grandchildren would have the timber they needed. The timber selection process also had spiritual dimensions that we shouldn't ignore or romanticize, but should acknowledge. The Vikings believed in spirits, in forces that inhabited the natural world. Trees, especially old, massive trees that had stood for centuries, were sometimes believed to house spirits or serve as dwellings for supernatural beings. Cutting such a tree wasn't just a technical decision, it was a spiritual act that required respect, sometimes ritual. Before felling a particularly significant tree, offerings might be made. A craftsman might pour a libation of mead or ale at the tree's base, asking permission or thanking the tree for its sacrifice. Whether this was genuine belief or simply tradition is impossible to know and probably varied from person to person. But it reflected a worldview that saw trees as more than just materials, as living beings that deserved acknowledgement, even as they were taken for human purposes. When the tree finally fell, when that massive trunk crashed to the earth with a sound like thunder, there was often a moment of silence, of acknowledgement. Something that had stood for perhaps 300 years, that had weathered countless storms and seen generations of humans come and go, had ended its growth. Now it would serve a different purpose, transform from living tree to ship component. In capable hands, the tree would continue its existence, not growing but traveling, not rooted but moving, experiencing the world in ways no rooted tree ever could. This philosophical approach might seem strange or overly romantic to modern sensibilities, but it reflected a practical truth. Respect for materials led to better craftsmanship. A shipwright who saw the tree as a gift to be honored worked more carefully than one who saw it as just a resource to be consumed. The former created ships that lasted decades. The latter created ships that failed. With the timber selected, processed, and ready, the real art of shipbuilding began. And it started with the keel. The keel was everything. It was the spine, the foundation, the structural element upon which the entire ship depended. Get the keel wrong and nothing else mattered. Every other piece of the ship attached to the keel, or to something that attached to the keel. If it was weak, twisted, or improperly shaped, the entire vessel would be compromised. The keel was carved from a single, massive piece of oak. No joints, no splices, one continuous piece running the entire length of the ship. For a large longship, this meant finding and processing an oak trunk, 60 or even 70 feet long. Such trees were rare, precious, and took centuries to grow. The keel represented an enormous investment of resources, just in the raw material, never mind the labor of shaping it. The keel's profile was distinctive, instantly recognizable to anyone familiar with Viking ships. It wasn't a flat plank. It was shaped like an elongate T or an upside-down V, with a narrow, deep profile that extended well below the hull. This shape served multiple purposes, all of them crucial. First, it provided lateral stability, preventing the ship from sliding sideways when sailing across the wind. Second, it protected the bottom of the hull when the ship ran aground on beaches or river bottoms, taking the abrasion instead of the delicate planking. Third, it provided a strong central structure to which all the ribs and planking could be attached. Shaping the keel was painstaking work, done entirely with axes and adzes. The shipwright worked slowly, removing material carefully, constantly checking the keel's straightness and symmetry. Any twist, any curve, any irregularity would be magnified when the rest of the ship was built. Hours turned into days, days into weeks. The shipwright ran his hands along the wood constantly, feeling for imperfections too small to see. He sighted along its length from multiple angles, checking for straightness. He measured, remeasured, adjusted, and refined. The keel needed to be not just straight, but also consistently shaped from end to end. The cross-sectional profile had to remain uniform, the depth and width proportional throughout the length. Variations would create weak points or affect how the ship moved through water. Modern tools, lasers, and measuring instruments make this easy. Viking shipwrights did it by eye, by feel, by experience, and they got it right consistently, reliably, creating keels that were straight to within fractions of an inch over lengths of 60 feet or more. Once satisfied with the keel shape, the shipwright began adding the stem and stern posts. These were the dramatic, often elaborately carved pieces that rose from the front and rear of the keel, giving Viking ships their distinctive profile. The stem post, rising from the bow, often curved forward and up, sometimes carved into the head of a dragon or serpent. The stern post rose at the back, usually more vertical but equally distinctive. These posts weren't just decorative, they were structural, bearing enormous loads as the ship flexed in the waves. The connection between keel and stem post was one of the most critical joints in the entire ship. The Vikings used a sophisticated scarf joint, cutting both pieces at precise angles so they interlocked and overlapped. The joint was then fastened with iron nails, or wooden tree nails, pegs driven through holes drilled precisely through both pieces. The joint needed to be invisible, seamless, as strong as the solid wood around it. A weak stem post connection meant the bow would eventually separate from the keel, a catastrophic failure that would sink the ship instantly. Creating the scarf joint required extraordinary precision. The angles had to match perfectly. The surfaces had to mate smoothly with no gaps. The holes for the fasteners had to be drilled at exactly the right angles and positions. Any error, any sloppiness would compromise the joint's strength. The shipwright worked carefully, testing the fit repeatedly, making tiny adjustments, ensuring perfection before permanent fastening. The stem post's curve was carefully calculated, though not through mathematical formulas. The shipwright knew from experience how much curve was needed to achieve the desired bow shape. Too vertical and the bow would pound into waves, making the ship uncomfortable and slow in head seas. Too angled and the bow would rise too easily, possibly causing the ship to pitch excessively or even submarine in following seas when waves came from behind. The optimal curve balanced these concerns, creating a bow that cut through waves efficiently, rose over swells smoothly, and remained controllable in various sea conditions. Different ship types had different stem post curves. Warships, designed for speed, had more aggressive curves. Merchant ships, designed for stability and cargo capacity, had gentler curves, but all followed the same basic principle, using the natural strength of curved oak to create a bow that could withstand years of pounding through North Atlantic swells. The stern post was equally important, though often less dramatically shaped. It rose from the rear of the keel, creating the ship's aft profile. Its angle and height affected how the ship handled, particularly when sailing downwind or in following seas. A well-designed stern post allowed water to flow smoothly past the rear of the ship, reducing drag and improving speed. A poorly designed stern post created turbulence and resistance, slowing the ship and making it harder to steer. Like the stem post, the stern post was scarfed to the keel, though the specific joint design sometimes differed. The forces at the stern were different from those at the bow, wave impacts less violent, but water flow more complex. The shipwright adapted his joinery to match the specific stresses each joint would experience. With the keel and posts in place, the basic profile of the ship was established. From the side, you could see the distinctive Viking ship silhouette, the long straight keel with dramatically rising posts at bow and stern. This skeleton would now be fleshed out with planking, and this is where Viking shipbuilding truly becomes remarkable. This is where the sophistication, the ingenuity, the obsessive attention to detail becomes undeniable. Most ships, throughout most of human history, have been built using what's called frame-first construction. You build a skeleton of ribs and supports, and then you attach the planking to that skeleton. It's logical, it's straightforward, it's what most people imagine when they think about shipbuilding. But the Vikings did it backward. They used clinker construction, also called lapstrake, building the shell first and adding the ribs later. They built from the outside in. They started with the keel and then attached planks directly to the keel, working their way up the sides of the ship. Each plank overlapped the one below it, creating a distinctive pattern of overlapping strakes that's instantly recognizable on Viking ships. Why build this way? Because it created a hull that was fundamentally different from anything else on the water. A clinker-built hull was lighter, stronger, more flexible, and more resilient than a frame-built hull. The overlapping planks created a structure where every plank supported and reinforced every other plank. The hull could flex and twist as waves passed under it without breaking. It could bend without cracking. It could absorb impacts without shattering. This flexibility was revolutionary. Other ships fought the sea, their rigid hulls trying to maintain shape against forces that wanted to break them. Viking longships moved with the sea, flexing and bending, absorbing and dissipating forces instead of resisting them. Sailors described longships as feeling alive in the water, as if the ship breathed with the waves. That wasn't poetic imagination, it was literal truth. The ships flexed visibly, measurably, constantly. The planking process required extraordinary precision, Each plank needed to be shaped so that its upper edge aligned perfectly with the lower edge of the plank above it. The overlap needed to be consistent, usually about an inch or two along the entire length. The planks couldn't be simply flat boards. They needed to curve in multiple directions simultaneously, following the compound curves of the ship's hull. Achieving this required incredible skill, endless patience, and an intuitive understanding of how wood behaves when bent and shaped. The shipwright shaped each plank individually, using axes to carve the rough profile and then smoothing it with smaller tools. He'd hold the plank against the hull, mark where it needed adjustment, remove it, shave a little more, test it again. This process repeated dozens, sometimes hundreds of times for a single plank. There were no plans, no blueprints, no mathematical calculations. The shipwright worked by eye, by feel, by experience accumulated over decades. He could see in his mind how the curves would compound, how the planks would stack, how the shape would emerge. The first plank attached directly to the keel, called the garboard strake, was particularly critical. It established the hull's initial curve, setting the pattern for all subsequent planks. If the garboard was wrong, if its curve wasn't quite right, every plank above it would be affected. The entire hull shape would be compromised. So the shipwright lavished attention on the garboard, shaping it carefully, testing it repeatedly, ensuring it was absolutely perfect before permanent attachment. The garboard had to transition from the keel's relatively flat bottom to the rising curve of the hillsides. This transition required a complex three-dimensional curve that's difficult to visualize and even harder to create. The plank had to twist slightly along its length, changing angle gradually from one end to the other. Creating this twist without breaking the wood or introducing weak points required using wood with just the right grain pattern, worked with just the right technique. Once the garboard was fitted and secured, the second strake was shaped to overlap it, then the third, then the fourth. Each strake built on the one below, gradually building up the sides of the ship. As the planking rose higher, the curves became more pronounced. The sides flared outward, increasing the ship's beam and creating the distinctive shape that made Longships so stable and seaworthy. The planks varied in width and thickness depending on their position in the hull. Lower strakes, those near the waterline and below, were typically thicker and narrower. They bore more stress and needed more strength. Upper strakes could be thinner and wider, reducing weight while still providing adequate strength. This variation in plank dimensions was another subtle refinement, another way Viking shipwrights optimized their designs for performance. The length of individual planks varied too. A single strake might be made from multiple planks joined end to end. These joints, called scarfs, were carefully crafted to maintain strength while creating a smooth, continuous line. The scarf joints were staggered, never aligned vertically between adjacent strakes. This staggering distributed stress and prevented the hull from having lines of weakness running vertically. Creating a good scarf joint in a plank required the same precision as the keel to stem joint, but on a smaller scale. The two plank ends were cut at matching angles, creating an overlap of 6 inches or more. The overlapped section was drilled for rivets, typically 3 to 5 per scarf depending on the plank size. When properly made, a scarf joint was as strong as continuous wood, virtually invisible, and contributed no weakness to the structure. The planks were fastened to each other at the overlaps using iron nails called rivets. But these weren't simple nails hammered through and bent over. They were carefully crafted, precisely sized, strategically placed. Each rivet was made by a skilled blacksmith, forged from iron, with a head on one end and a shaft just long enough to pass through both planks, with a small amount protruding on the inside. The installation process was exacting. First, the shipwright marked where each rivet should go, spacing them evenly along the overlap. Then holes were drilled through both planks. The drilling was done carefully, at a slight angle so the rivet would pull the planks together when fastened. The rivet was then driven through from the outside. On the inside, a small metal washer called a rove was slipped over the protruding shaft. The end of the shaft was then hammered, spreading it outward and locking the rove in place. The result was a permanent, unbreakable connection that pulled the two planks tightly together. The spacing and placement of rivets was critical. Too few, and the planks would pull apart under stress. Too many, and you weakened the wood by drilling too many holes. The The Vikings found the optimal balance through generations of experience and occasional catastrophic failures that taught brutal lessons. Typically, rivets were spaced about 6 inches apart along the overlap, close enough for strength, far enough apart to preserve wood integrity. The quality of the rivets themselves mattered enormously. Poor iron with inclusions or impurities would create weak rivets that might fail under stress. The blacksmiths who made rivets for ships were specialists, highly skilled craftsmen who understood that lives depended on their work. They selected their iron carefully, heating and hammering it repeatedly to remove impurities and align the grain structure. They shaped each rivet carefully, ensuring the head was properly formed and the shaft was straight and uniform. Modern analysis of Viking ship rivets, examining ones recovered from archaeological sites, reveals sophisticated metallurgy. The iron is remarkably pure by medieval standards. The forging is expert, creating rivets that remain strong for centuries. Some rivets show evidence of case hardening, a technique that hardens the surface while leaving the core softer and more resistant to shock. Whether this was intentional or a fortunate side effect of the forging process is uncertain, but it demonstrates the sophistication of Viking metalworking. But rivets alone weren't enough to make the seam watertight. Water would seep between the planks, slowly but inevitably flooding the ship. The Vikings solved this with caulking, stuffing the seams with material that would swell when wet, creating a watertight seal. They used animal hair, usually from cows or horses, mixed with tar. The hair was twisted into long cords and pressed into the grooves between planks before the rivets were driven. When the ship entered water, the organic material absorbed moisture, expanded, and sealed the gaps. The tar made it sticky, helping it adhere and preventing it from washing out. The caulking process was tedious, unglamorous, and absolutely essential. Every seam, every overlap, every joint had to be caulked carefully. Miss a section and the ship would leak. Use too little and it wouldn't seal. Use too much and it would prevent the planks from fitting together properly. Again, this was craft knowledge, learned through practice, refined through experience. The tar itself was another specialized product. It came from pine trees, extracted by heating pine wood or pine stumps in earth-covered kilns that allowed the resin to melt and drain out while preventing complete combustion. Collecting enough tar for a ship required significant effort and time. A large longship might need hundreds of pounds of tar for caulking, treating the lower hull to prevent rot, and various other waterproofing applications. Some regions developed reputations for producing superior tar. Norwegian tar, particularly from certain forested regions, was highly prized for its consistency and waterproofing qualities. Communities with access to good tar sources could trade it for other goods, or they used it to enhance the quality and reputation of the ships they built. Tar barrels became common trade goods, moved along Viking trade networks throughout the Baltic and North Sea. As the planks built up the sides of the ship, the hull began to take shape, and the shipwright constantly assessed the curves, the symmetry, the proportions. Viking ships had beautiful, graceful lines, not by accident or aesthetic preference alone, but because those curves were hydrodynamically efficient. The bow was sharp and high, cutting through waves and allowing the ship to ride over swells instead of plowing through them. The sides flared outward, creating stability and increasing the ship's carrying capacity. The stern was slightly less sharp than the bow, but still streamlined, allowing water to flow smoothly past. The cross-section was carefully considered. Too flat and the ship would be unstable, rolling violently in any waves. Too rounded and it would be slow, unable to sail efficiently. The Vikings found the sweet spot, a gentle curve that provided stability without sacrificing speed. Different ship types had different curves. Warships, designed for speed and shallow draft, were narrower and more curved. Trading ships, designed for cargo capacity, were wider and flatter, but all shared the same basic principles, the same obsessive attention to hydrodynamic efficiency. The shipwright didn't work alone during planking. He typically had one or more experienced assistants, plus several apprentices. The work was carefully coordinated. While the master shipwright shaped the next plank, assistants might be drilling rivet holes in the previous plank, checking alignment, or preparing caulking material. Apprentices fetched tools, sharpened axes, and performed routine tasks under supervision. Everyone had a role, everyone contributed, and everyone understood that the ship's quality depended on every person doing their job correctly. The pace of work varied with the seasons. Summer, with its long daylight hours, allowed extended workdays. The shipwrights worked from dawn until dusk, taking breaks for meals but otherwise laboring steadily. Winter, with short days and bitter cold, slowed progress dramatically. Some work stopped entirely during the coldest months. Other work continued, but at a reduced pace. The shipwright might use winter for tasks that could be done indoors or in partial shelter, shaping smaller components, making tree nails, preparing stock materials for spring. The construction site itself was usually located near water, but above the high tide line, on a beach or riverbank, where the completed ship could be easily launched. The keel was supported on blocks or logs that held it level and at a comfortable working height. As the hull grew, additional supports were added to prevent it from toppling or distorting. The entire structure had to remain perfectly aligned throughout construction, with no twisting or sagging that would compromise the final shape. Around the construction site, piles of wood chips and shavings accumulated as the shipwrights shaped thousands of pieces. These shavings weren't wasted. They were collected and used for fire starting, animal bedding, or even insulation in homes. In a resource-limited society, nothing went unused if it had any value at all. The smell of the construction site would have been distinctive. Fresh-cut oak has a sharp, tannic smell. Pine tar added a sweet, resinous scent. The wood smoke from fires used for heating tar or warming workers in cold weather mixed with these other smells, creating an aroma that probably became familiar and comforting to the shipwrights, associated with their craft and their contribution to the community. Once the planking was complete up to the desired height, usually somewhere between 10 and 16 planks per side depending on the ship's size, the hull was essentially finished. Only then did the shipwright begin adding the internal structure, the ribs and cross beams that would give the shell its final strength and provide supports for the deck, mast and rowing benches. And here's where clinker construction's genius truly shines, because the ribs weren't load-bearing in the same way they were in frame-first construction. The shell, the overlapping planks, provided most of the structural strength. The ribs reinforced and stiffened the hull, preventing it from distorting, but they didn't carry the primary loads. This meant the ribs could be lighter, more flexible, more carefully shaped to follow the hull's curves without fighting them. The ribs were shaped from naturally curved pieces of oak, chosen during the initial timber selection for their appropriate curves. The shipwright would carefully fit each rib to the hull's interior curve, shaping it until it made full contact with the planking. Then, instead of nailing the ribs directly to the planks, which would create hard points that could crack the planking, the Vikings used a brilliant solution. They tied the ribs to the planks using cordage made from roots, usually spruce roots, that passed through small holes drilled through the planks and wrapped around the ribs. This lashing system allowed the hull to flex without the ribs and planks grinding against each other or creating stress concentrations. The cordage absorbed shock, distributed loads, and allowed the entire structure to move as a unified whole. It was flexible joinery, biomimetic before anyone had coined the term, creating a structure that behaved more like a living organism than a rigid machine. The process of installing ribs began after the hull planking was complete. The shipwright would place a rib inside the hull, position it carefully, and mark where the lashing holes needed to be drilled. The holes were drilled from the outside, passing through the plank, but not completely through the rib on the inside. The spacing of holes was carefully planned, typically 2 to 4 per rib, depending on the rib's height and the forces it would experience. The lashing itself was an art. Spruce roots were harvested in spring, when sap flow made them easier to separate from the surrounding soil. The roots were cleaned, split if necessary, to achieve the desired thickness, and often soaked to make them pliable. The lashing technique varied slightly from region to region and from shipwright to shipwright, but the goal was always the same: create a secure connection that allowed some flexibility while preventing the rib from separating from the planking. One common method involved passing the root through a hole, wrapping it around the rib in a specific pattern, passing it through an adjacent hole, and repeating. The pattern distributed the forces and prevented any single point from bearing all the stress. When properly done, The lashing was incredibly strong, capable of holding the rib firmly while still allowing the natural flex that made clinker-built hulls so resilient. As the ribs were installed, moving from bow to stern, the hull gained rigidity and began to feel like a complete structure rather than just a shell. The shipwright constantly checked that the hull maintained its proper shape, that the ribs weren't pulling or pushing the planking out of alignment. Small adjustments might be needed, a rib shaved slightly to fit better, a lashing tightened or loosened, ensuring perfect conformation between hull and ribs. The cross beams, called thwarts or beams, stretched from side to side, providing lateral support and serving as seats for the rowers or supports for the deck. These were mortised into the hull planking through reinforced sections called knees, L-shaped pieces of naturally curved wood that distribute loads. The knees were some of the most carefully selected pieces in the entire ship because they had to be strong, perfectly curved at roughly 90 degrees, and resistant to the enormous sideways forces the rowing and sailing generated. A knee was carved from a section of oak where the trunk met a major branch, creating a natural L shape with grain running continuously through the curve. This continuous grain meant the knee wouldn't split at the angle where forces concentrated. The knee was carefully shaped to fit precisely against both the hull side and the beam, creating maximum contact and distributing forces across the largest possible area. The beams themselves varied in size and spacing depending on their purpose. In warships, where rowing was the primary propulsion for tactical situations, beams were spaced at regular intervals corresponding to rowing positions. Each beam served as the base for a rowing bench or rowing position. In merchant ships where cargo capacity mattered more, beams might be spaced less regularly, positioned to provide structural support while leaving larger open areas for cargo storage. The beam installation was critical for maintaining the hull's shape. The beams prevented the hull sides from spreading outward under the pressure of water and cargo. They also kept the hull sides from collapsing inward if the ship were hauled out of water or beached. Essentially, the beams locked the hull's width, making the structure rigid transversely, even as it remained flexible longitudinally. Installing beams required precision. The mortises cut into the hull planking had to be exactly positioned, perfectly aligned port and starboard, so the beam would sit level. The fit had to be tight without being forced, allowing the beam to be installed without splitting the planking, but secure enough that it wouldn't work loose under stress. The knees were fastened with tree nails, wooden pegs driven through holes drilled through knee, plank and beam, creating a mechanical connection that couldn't pull apart. Tree nails deserve their own explanation because they were sophisticated fasteners, not just simple wooden pegs. A tree nail, also called a tree nail or trunnel, was carefully made from a different wood than the ship's primary structure. Oak planking and ribs were usually fastened with willow or pine tree nails. The different wood species expanded and contracted at different rates with changes in humidity, actually creating tighter joints as the wood moved. A tree nail was shaped from a straight-grained piece of wood, roughly cylindrical, slightly tapered from one end to the other. The taper was subtle but intentional. The hole drilled to receive the tree nail was also slightly tapered, matching the tree nail's taper. This meant that as the tree nail was driven in, it fit progressively tighter, wedging itself firmly in place. Once fully seated, the protruding ends were often split and wedged, creating a mechanical lock that prevented the tree nail from backing out. The tree nail's wood swelled when wet, creating even tighter connections. But unlike iron rivets, tree nails had some give, some flexibility. They could absorb shock without shattering or pulling through the wood. In a structure designed to flex, tree nails were often superior to rigid metal fasteners, providing secure connections without creating stress concentrations. The deck, if the ship had one, was usually partial, covering only the bow and stern, leaving the central section open. This kept weight low, improved flexibility, and made it easier to manage cargo, bail water, and move around during battle. The deck planks were removable, not permanently attached, making it easy to access the hull below for maintenance or to reconfigure the ship for different purposes. The deck planks were laid across the beams and held in place primarily by their own weight and sometimes by simple wooden cleats. This removability was crucial for maintaining the ship. If a hull plank needed repair, the corresponding deck planks could be lifted out, providing full access. If the ship needed to carry an unusual cargo, deck sections could be removed to create more open space. In the bow and stern, where deck coverage was permanent, the planking was typically fastened more securely to the underlying beams. These areas provided shelter for supplies, sleeping space for crew on long voyages, and protected areas for valuable cargo. The bow deck in particular often included a small enclosed space where important items could be stored with some protection from weather and waves. Throughout this process, the shipwright constantly assessed, adjusted, and refined. He ran his hands over surfaces, feeling for rough spots, irregularities, misalignments. He sighted along curves, checking symmetry. He pushed and pulled on joints, testing strength. He was building not just a ship, but a life support system for crews that would trust it with their lives in some of the most dangerous waters on Earth. The construction process took time. Building a medium-sized longship required several months of focused labor by multiple skilled craftsmen and many more helpers. A large warship might take a year or more, but the Vikings didn't rush. They understood that speed in construction meant death at sea. Better to take the time, do it right, and launch a ship that would serve for decades. Because that's another remarkable fact about Viking longships. They lasted. Ships that were properly built and maintained could serve for 20, 30, even 50 years. Excavated longships show evidence of repairs, modifications, and upgrades, suggesting they were valued possessions, carefully maintained and treated with respect. This wasn't disposable technology. These were heirloom tools, passed from generation to generation, each voyage adding to their history and reputation. The completed hull, before any fittings or propulsion systems were added, was a beautiful object in its own right. The fair curves, the precise overlaps of the strakes, the elegant sweep from stem to stern, all testified to the skill of the craftsman who created it. Even unpainted, even without decoration, the naked hull was sculpture, functional art created not for display but for purpose. But the hull was just the beginning. A ship without propulsion is just an expensive floating box at the mercy of currents and winds. Viking longships needed two methods of propulsion: oars for maneuvering in tight spaces, fighting currents, and operating when wind was absent or unfavorable, and sails for long-distance travel, for crossing open water where rowing would exhaust any crew. The oars were simpler than you might expect, but carefully designed nonetheless. Each oar was carved from a single piece of wood, usually pine or ash, chosen for its straight grain and light weight. A longship's oars were long, typically 15 to 18 feet, with narrow blades designed to enter and exit the water cleanly with minimal resistance. The oars needed to be light enough to row for hours without exhausting the crew, but strong enough to withstand the enormous forces generated by powerful strokes in heavy seas. The oar's balance was critical. Too much weight in the blade and the oar would be exhausting to lift on the recovery stroke. Too much weight toward the handle and it would be hard to control. The Vikings carved the shaft with subtle thickness variations, making it slightly thicker near the middle where it rested against the oar port and tapering toward both ends. This created an oar that was strong at the fulcrum, where bending forces were greatest, but light at the extremes, where reduced weight minimized fatigue. Shaping an oar required understanding wood behavior and rowing mechanics. The blade needed to be shaped with subtle concavity, a slight dish that helped it grip the water and prevented it from fluttering or slipping during the power stroke. But too much concavity created excessive drag and made the oar harder to recover. The optimal shape was subtle, almost imperceptible to the eye, but noticeable to experienced rowers. The shaft was typically oval in cross-section rather than round, providing better grip and preventing the oar from rotating in the rower's hands. The end that the rower held might be slightly shaped to fit the hands comfortably, with gentle curves that allowed a secure grip without sharp edges that would cause blisters. Each oar was an individual piece, custom shaped for its specific position in the ship. Oars near the bow and stern, where the hull was narrower, were often slightly shorter than a midship's oars. This ensured that all oars could move through their complete range of motion without striking each other or the hull. A set of oars for a large longship represented significant work, potentially 40 or more individual pieces, each requiring hours of shaping and finishing. The oar ports, the holes through which the oars passed, were cut through the planking near the top of the hull. These weren't just round holes, they were carefully shaped slots, sometimes lined with leather, designed to allow the oar to pivot up and down and rotate slightly without jamming or leaking excessively. The shape was typically a narrow oval or slot, just wide enough for the oar shaft with minimal clearance. The placement of oar ports was carefully calculated during the hull design phase. They had to be high enough above the waterline that waves wouldn't constantly wash through them, but low, enough that the oars could reach the water efficiently. They also had to be positioned in the hull where the planking was strongest, typically along a strake that was reinforced internally with additional bracing. When not in use, the oar ports could be closed with wooden plugs or shutters, preventing water from splashing in during rough weather or when under sail. These closures were simple but effective, often just shaped wooden pieces that fit snugly into the ports and could be quickly removed when oars were needed. The rowing positions were carefully planned. On a typical longship, rowers sat on sea chests that doubled as storage for personal belongings and cargo. This dual-purpose design was brilliant, maximizing the use of limited space. A sea chest was typically a simple wooden box, about 2 feet long and perhaps 18 inches wide and high, secured to the ship but removable if needed. The spacing between rowers was standardized, typically about 3 feet, giving each rower enough room to work without interfering with his neighbors. The rhythm of rowing was crucial. An experienced crew developed a cadence, timing their strokes to work with the ship's motion, pulling hard as the ship rose on a wave, feathering the blades on the recovery as it dropped into the trough. But oars, as effective as they were, had limitations. Rowing was exhausting. Even a strong crew could only maintain rowing speed for a few hours before fatigue set in. For long voyages, for crossing open ocean, for traveling the vast distances that defined Viking expansion, the longship needed its most distinctive feature, the sail. The mast was an engineering challenge all its own. It needed to be tall enough to carry a large sail capable of driving the ship at speed. It needed to be strong enough to withstand enormous forces, wind loads that could easily reach several tons in a strong breeze, and critically, it needed to be removable. Viking ships were designed to navigate shallow rivers and be pulled up onto beaches. A fixed mast would make this impossible, constantly snagging on obstacles and making the ship ungainly. The solution was the mast step and mast partner system. The mast step was a heavy wooden block, often carved from a single piece of oak, set low in the ship's hull near the keel. It had a socket carved into it, shaped to receive the foot of the mast. This socket was usually rectangular or slightly tapered, ensuring the mast couldn't rotate once seated. The mast partner was a heavy beam stretching across the ship at deck level, with a hole through which the mast passed. Together, the step and partner held the mast firmly vertical and transferred the enormous lateral loads generated by the sail down into the ship's structure. The genius was in making this removable without sacrificing strength. The mast could be lifted out of the step and lowered, sometimes in minutes, by releasing the stays, lifting the mast and pivoting it back along the length of the ship. This allowed the ship to pass under low bridges, to navigate shallow waters where a tall mast would be visible for miles, and alert victims to the Vikings' approach, and to reduce wind resistance when rowing. The mast itself was typically made from a single tall pine, chosen for its straightness and lack of knots. A large long ship might have a mast 40 feet tall or more, supporting a sail with an area of several hundred square feet. The mast was carefully shaped, thicker at the base where bending forces were greatest, tapering toward the top where less strength was needed, and reduced weight improved stability. Finding a suitable pine for a mast was almost as difficult as finding oak for the keel. The tree needed to be tall, straight, and relatively free of branches for the lower 30 or 40 feet. Such trees typically grew in dense forests where competition for light forced upward growth with minimal branching. Coastal regions often lacked such trees, meaning mast timber sometimes had to be transported from inland forests, adding to the cost and complexity of shipbuilding. Shaping the mast was laborious but straightforward compared to shaping hull planks. The primary concern was removing enough wood to reduce weight while maintaining adequate strength. The shipwright worked systematically, starting with the thickest section at the base and gradually reducing diameter toward the top. The taper wasn't uniform. It was calculated, steeper near the base, where weight reduction mattered less, gentler near the top, where every bit of strength was needed to handle the sail's forces. The foot of the mast, the part that seated in the mast step, was shaped to match the step's socket precisely. Any gap or looseness would allow the mast to shift under load, potentially damaging both the mast and the step. The fit had to be snug, almost tight, requiring some force to seat the mast initially, but secure once in place. The top of the mast needed different treatment. Here, the shipwright installed a block or sheave through which the halyard passed. The line used to raise and lower the yard and sail. This block had to be carefully installed, its axle passing through the mast in a way that didn't weaken the wood. The hole for the axle was carefully positioned and reinforced, sometimes with iron bands wrapped around the mast to prevent splitting. The yard, the horizontal beam from which the sail hung, was another carefully crafted piece. It needed to be long, often nearly as wide as the ship, and strong enough to support the sail's weight and handle the forces the wind exerted. The yard was typically made from a single piece of wood, though on the largest ships, two pieces might be scarfed together. Like the mast, the yard was tapered, thickest in the middle, where the mast attachment point bore the greatest loads, thinner toward the ends. The ends often featured shaped blocks or fittings where lines attached for controlling the sail. These fittings had to be strong, enough to handle forces that could reach hundreds of pounds without splitting the yard or pulling loose. The yard was attached to the mast with a complex arrangement of lines and fittings that allowed it to be raised and lowered, pivoted to adjust sail angle, and secured firmly when underway. The primary attachment was typically a large wooden block or metal fitting that encircled the mast and attached to the yard's midpoint. This fitting allowed the yard to slide up and down the mast as it was raised or lowered, but prevented it from separating from the mast or twisting unpredictably. And then there was the sail itself. This was perhaps the single most expensive component of the entire ship. Viking sails were enormous pieces of woven wool, typically rectangular, measuring 30 to 40 feet wide and 40 to 50 feet tall for a large ship. The wool came from sheep, naturally, but not just any wool. It needed to be long staple, strong, and tightly woven to withstand the forces the wind would exert. The weaving process was intensive, time-consuming, and required skilled labor. Women typically did this work, spending months or even years creating a single sail. The loom needed to be enormous, specially built to handle the sail's size. Setting up such a loom was itself a significant undertaking, requiring substantial space and carefully engineered support structures to handle the tension of the woven fabric. The wool was first sheared, cleaned, and processed to remove impurities. Then it was spun into yarn, a process that created thread of consistent thickness and strength. The spinning was done with hand spindles, or in some cases, primitive spinning wheels, each skein of yarn representing hours of careful work. The weaving itself was done in sections. The loom couldn't handle the entire sail at once, so the fabric was woven in strips, each perhaps 3 to 4 feet wide, which were then sewn together to create the final sail. The seaming of these strips required its own expertise, using strong stitching techniques that wouldn't tear under the forces the sail would experience. The weave pattern mattered. Too loose and the sail would stretch excessively, distorting its shape and losing efficiency. Too tight and it would be unnecessarily heavy and might not handle flexing well. Viking weavers developed optimal weave patterns through generations of experience, creating fabric that balanced strength, weight, and flexibility. A completed sail might weigh several hundred pounds, a massive investment of labor and materials. The value of a sail was often as much or more than the rest of the ship combined, reflecting the enormous labor required to create it. Losing a sail in a storm wasn't just inconvenient, it was economically devastating, potentially taking years to replace. But wool, even tightly woven, isn't waterproof. A wet wool sail becomes incredibly heavy, stretching and distorting under its own weight. So Viking sails were treated with fat, oil, or other substances that help shed water and preserve the fibers. Animal fat, particularly from seals or fish, was commonly used. The fat was rendered and applied to the sail, sometimes by soaking, sometimes by careful application with brushes or cloths. The treatment process made the sail somewhat water resistant, causing water to bead and run off rather than soaking in. It also helped preserve the wool fibers from rot and degradation caused by constant exposure to salt water. A treated sail lasted much longer than an untreated one, though it required retreatment periodically as the protective coating wore away. Red and white sails were common, created by using different colored wools or dyeing the finished fabric. Some sails featured stripes or patterns, possibly identifying the ship's owner or serving as recognition symbols. The dyes came from various sources: red from madder root or crushed insects, yellow from weld or other plants, blue from woad, though blue was less common, possibly because good blue dyes were more expensive or difficult to produce. The sail's shape and cut were critical to performance. A sail that was too flat wouldn't capture wind efficiently. A sail that was too baggy would spill wind and lose power. The Vikings developed sophisticated sail shapes with subtle curves built in, allowing the sail to maintain an efficient airfoil shape when filled with wind. These curves were created during the weaving and assembly process, carefully calculating how the fabric would hang and distort under wind pressure. The edges of the sail were reinforced with extra layers of fabric or leather, preventing tearing at the stress points where the ropes attached. Corner reinforcements were particularly heavy, sometimes featuring multiple layers of material and even leather patches that distributed loads across larger areas. The bolt rope, a heavy line sewn along the sail's edges, provided additional strength and an attachment point for various control lines. The bolt rope was carefully sewn using techniques that allowed it to be replaced if it wore out without requiring the entire sail to be replaced. This repairability was crucial, as sails needed to last for many years and inevitably suffered wear and damage. The rigging, the complex network of ropes that controlled the sail, was another specialized craft. Different types of ropes served different functions. The halyard, which raised and lowered the yard and sail, needed to be strong and smooth running. A typical halyard might be an inch or more in diameter, made from the strongest available materials. The sheets, which controlled the sail's angle to the wind, needed to be strong, but also flexible enough to be adjusted quickly. These lines ran from the lower corners of the sail through blocks or fairleads to positions where crew members could reach them easily. Adjusting the sheets changed how the sail captured wind, allowing the ship to sail at different angles relative to the wind. Direction. The stays, which prevented the mast from falling over, needed tremendous strength to resist the forces trying to pull the mast forward or backward. The forestay ran from the top of the mast to the bow, while the backstay ran to the stern. These weren't single ropes, but heavy cables, often made from twisted walrus hide or braided horsehair, both materials that were strong, durable, and resistant to rot when constantly wet. Viking rope was typically made from walrus hide, horsehair, or sometimes hemp, though hemp was less common in Scandinavia and often had to be imported. Walrus hide rope was particularly prized for its strength and durability. Creating it required carefully cutting walrus hides into long strips, often in a spiral pattern that could produce strips 50 or more feet long from a single hide. These strips were then twisted or braided together to create rope of the desired thickness. Horsehair rope was lighter than hide rope and more flexible, making it suitable for lighter duty applications. Creating horsehair rope required collecting hair from many horses, sorting it by length and quality, and then carefully twisting it into strands that were then combined into rope. The process was laborious, but the resulting rope was strong and handled well. The rope was twisted or braided, creating strong lines that could handle enormous loads. The thickness varied depending on purpose. Stay ropes might be several inches thick, while control lines were thinner and more flexible. The twist direction even mattered. Rope twisted in one direction behaved differently than rope twisted in the opposite direction, and experienced sailors knew which type worked best for each application. The blocks and tackle, simple pulley systems that provided mechanical advantage, allowed a few sailors to control enormous forces. These were carved from wood with grooved wheels that let rope run smoothly. The blocks were often made from hardwoods like ash or beech, carved, carefully to create smooth surfaces that wouldn't fray the rope passing through them. The blocks themselves were sophisticated devices. A good block featured closely matched bearing surfaces, minimal friction, and secure attachment points. The sheave, the wheel inside the block, was carefully shaped with a groove that matched the rope's diameter, preventing the rope from jamming or wearing excessively. The axle on which the sheave rotated was often made from hardwood or even bone, materials that were smooth and resistant to wear. Oil or fat was used as lubricant, keeping everything moving freely even when soaked with salt water. Regular maintenance of the rigging was essential. Blocks needed to be inspected, cleaned, and relubricated. Ropes needed to be checked for wear, with damaged sections cut out and replaced before they failed under load. The steering mechanism deserves special attention because it was uniquely Viking. Instead of a rudder hung from the stern, which was the norm. In later ship designs, Viking ships used a side-mounted steering oar, always on the starboard side. Starboard, incidentally, comes from the Old Norse stjornbordi, literally steering side. The steering oar was essentially a large, specially shaped oar mounted on the side of the ship near the stern. But calling it an oar understates its sophistication. It was carefully designed to provide maximum steering effect with minimum drag. The blade was shaped with an asymmetric profile, thicker on one edge, thinner on the other, creating a foil shape that generated lift when angled relative to the water flow. This made the ship more responsive to steering inputs and allowed the helmsman to hold a course with less effort. The steering oar was attached with a sophisticated arrangement of leather straps and wooden supports that allowed it to pivot, but held it firmly in place against the enormous forces of water flowing past the moving ship. The mounting system had to be robust enough to handle these forces while still allowing the helmsman to move the oar for steering. Balancing these requirements required careful design and quality materials. The primary attachment was typically a leather strap or series of straps that passed around the steering oar's shaft and attached to a block or reinforced section of the hull. The leather provided some flexibility, absorbing shock and allowing the steering oar to rise slightly if it struck a submerged object, rather than being torn off or damaging the hull. The helmsman controlled it with a tiller, a horizontal bar attached to the top of the steering oar that could be pushed or pulled to pivot the blade and change the ship's direction. The tiller was positioned so the helmsman could operate it while having clear visibility forward and the ability to communicate with the rest of the crew. On some ships, the helmsman stood. On others, there might be a simple seat or support. This side mounting might seem primitive, but it had advantages. The steering oar could be quickly unshipped, removed entirely, when beaching the ship or in very shallow water. This was crucial for Viking operations, which often involved navigating shallow rivers or pulling ships onto beaches. A stern-mounted rudder would have been damaged or broken in these situations. The steering oar was also easier to repair or replace than a stern-hung rudder. If damaged, it could be unshipped, repaired or replaced and reinstalled, all without major structural work to the ship. This repairability was important for vessels that might be operating far from home waters, with limited access to shipwrights and materials. And in skilled hands, it provided precise control. Viking helmsmen could perform remarkably sophisticated maneuvers, threading their ships through narrow channels, spinning in place by using the steering oar in combination with differential rowing, and even sailing backward when necessary. The steering oar's responsiveness and the helmsman's skill combined to make longships remarkably maneuverable despite their length. The entire propulsion system, oars, mast, sail, rigging, and steering, worked together as an integrated system. The crew could adjust tactics based on conditions. In rivers and harbors, they rowed, the sail furled and mast perhaps lowered. On the open ocean with favorable winds, they sailed, the oars secured and the crew resting. When wind and conditions allowed, they might do both, rowing and sailing simultaneously to maximize speed. This versatility was revolutionary. Most other ships were either rowing vessels or sailing vessels, good at one mode of propulsion, but terrible at the other. The longship excelled at both. It could outsail sailing ships in light winds because of its efficient hull shape and large sail area relative to its displacement. It could outrow rowing ships because of its lightweight construction and optimized oar positions. and it could seamlessly transition between modes, taking advantage of whatever conditions offered. The result was a ship that could appear anywhere, anytime, traveling vast distances faster than anyone thought possible. Victims of Viking raids often reported that the ships seemed to come from nowhere, moving with impossible speed. That wasn't magical. It wasn't even exaggeration. It was engineering. The Longship was simply the most sophisticated, best-designed vessel in the medieval world, and its capabilities seemed supernatural to those who didn't understand the craft behind them. When a Longship was finally completed, when the last plank was riveted, the last seam caulked, the mast stepped, the sail bent on, and the oars fitted, what the shipwright had created was more than a vessel. It was the culmination of hundreds of years of accumulated knowledge. It represented an understanding of materials, forces, and design that was empirical, practical, and profoundly sophisticated. And every single one was unique. No two Longships were identical. Each was built by hand, shaped by eye, adjusted by feel. The measurements and proportions were similar, following established practices and successful designs. But the details, the exact curves, the specific choices, the subtle refinements varied from ship to ship and shipwright to shipwright. This uniqueness meant ships had personalities. Sailors could feel differences, know that one ship was faster in light winds, another more stable in heavy seas, a third particularly responsive to the helm. These weren't imaginary differences. They were real variations resulting from the countless small decisions made during construction. And experienced Vikings learned these personalities, developing preferences and reputations. Give me a ship from Magnus's yard, those are always fast. I'd trust a ship from Uppsala for a North Atlantic crossing. These weren't superstitions, they were assessments of quality and design approaches that varied subtly between regions and shipwrights. The testing and refinement process continued even after launch. A new ship's first voyages were carefully monitored. How did it handle in various sea states? Did it have a tendency to round up into the wind or fall off? Was it tender, heeling easily, or stiff, resisting heel? Did it ship water over the bow in heavy weather? Was it quick to answer the helm or sluggish? Based on these observations, modifications might be made. Ballast might be added or redistributed. The mast position might be adjusted slightly forward or aft. Additional stiffening might be installed internally. The sail's shape might be altered. This iterative refinement continued throughout the ship's life, each voyage teaching lessons that could be applied as modifications or as knowledge for the next ship built. The relationship between shipwright and crew was often close. The shipwright took pride in his creation and wanted to know how it performed. Crews understood that the shipwright's skill directly affected their safety and success. A good shipwright was celebrated, sought after, and compensated well. A poor shipwright found himself without commissions and perhaps without a place in the community. This social pressure ensured quality control more effectively than any formal inspection process. Reputation was everything. A shipwright who produced consistently good ships became famous, his services in demand. A shipwright whose ships failed or disappointed was finished. The market for ships was small enough that everyone knew who built which ships and how they performed. There was no hiding from poor workmanship. The launch of a completed ship was a community event, often accompanied by ceremony and celebration. The ship represented a massive investment of community resources, the timber, the labor, the materials. Getting to launch day meant that investment had reached fruition. The ship was about to validate all that effort, or in some cases reveal that mistakes had been made. The actual launch, getting the ship from its construction site into the water, required careful planning. The ship might weigh several tons even before cargo, crew, and equipment were aboard. Moving it required coordinated effort. Often log rollers were placed under the keel, and the ship was pushed or pulled down a slight slope into the water. Sometimes launching coincided with high tide, allowing the rising water to lift the ship off its supports. The moment the ship first floated was critical. Would it sit properly in the water? Would it list to one side, indicating improper weight distribution or asymmetric construction? Would it draw the expected depth, or had the shipwright miscalculated? Would it leak, or had the caulking been done properly? These were tense moments. A ship that didn't float properly was a disaster, representing months or years of wasted effort. Fortunately, experienced shipwrights rarely made gross errors, but small issues were common and expected. A slight leak that could be easily corrected, a trim that needed adjustment with ballast. These were considered normal, addressed quickly before the ship entered service. Once afloat and deemed satisfactory, the ship underwent outfitting. Equipment was loaded. The sail, which had been protected during construction, was bent onto the yard. Oars were fitted. Provisions and supplies were stowed. The crew that would sail it familiarized themselves with its layout and characteristics. And then, finally, it was ready for its first real voyage. That first voyage was a shakedown, a test under real conditions. The ship would be taken on a relatively short trip, perhaps just along the coast or up a nearby river. Everything would be monitored carefully. How did it perform under oar? How did it handle under sail? Did anything work loose or fail? Were there any leaks that hadn't been apparent during trials at the dock? Based on this shakedown, final adjustments would be made. A block might be repositioned for better. Rigging leads. A troublesome leak might be recaulked. Ballast might be redistributed. And then the ship would be declared ready for full service, available for trading voyages, raids, exploration, or whatever purpose it had been built for. And once in service, the maintenance never stopped. Ships required constant care to remain seaworthy. Caulking dried out and needed replacement. Planks damaged by impacts or simply by years of flexing needed repair. Rigging wore and needed to be inspected and replaced before failure. The constant battle against rot, checking timbers, replacing affected sections before the rot spread, was ongoing. Good crews maintained their ships obsessively. They understood that their lives depended on the ship's integrity. After every voyage, there would be maintenance, inspecting the hull for damage, checking the caulking, examining the rigging, testing the mast and yard for cracks or weakness, cleaning out bilge water and debris. This work was unglamorous but essential. Ships were often deliberately beached and pulled out of the water for maintenance. This allowed access to the entire hull, particularly the underwater sections that were impossible to inspect while afloat. Beached, the ship could be thoroughly examined, damaged planks replaced, caulking renewed, and protective treatments applied to prevent rot and marine growth. The treatments varied. Pine tar was commonly applied to underwater sections, creating a protective coating that discouraged barnacles and other marine organisms from attaching. Animal fat or oil might be used above the waterline. Some ships were even smoked, hung over fires that filled the interior with thick smoke that helped preserve the wood and discourage insect infestation. These maintenance practices meant that Viking longships, despite being built entirely of organic materials that naturally deteriorate, could last for decades. Ships were valuable, carefully maintained assets, not disposable items. A ship that served for 30 years might have had numerous planks replaced, been recaulked dozens of times, had its rigging replaced multiple times, perhaps even had its mast replaced. The ship of Theseus paradox was literally lived by Viking crews. At what point had so many parts been replaced that it was no longer the same ship? The Vikings didn't worry about such philosophical questions. As long as it floated and sailed, it was the ship they depended on, the ship that had carried them safely through countless voyages. The knowledge embedded in these ships was far more sophisticated than written descriptions can fully capture. Modern attempts to reconstruct Viking shipbuilding techniques, while successful in creating vessels that work, probably miss subtle refinements and tricks that were obvious to period craftsmen, but weren't recorded because they were considered too basic to mention. We know Viking shipwrights didn't use written plans or detailed drawings. They worked from knowledge, passed down orally and through demonstration. This means that much of their understanding was tacit knowledge, knowledge that exists in the hands and eyes and minds, but is difficult or impossible to articulate explicitly. A modern shipbuilder trying to recreate a longship can follow archaeological evidence, use the same materials, employ similar techniques. But unless he's spent decades learning the craft, absorbing the subtle understanding that comes only with endless practice, he's missing something. He's following a recipe without understanding why each ingredient matters, what variations are possible, how to adjust when conditions aren't ideal. This is why the master-apprentice system was so crucial. It transmitted not just techniques but understanding. An apprentice who spent 20 years learning the craft absorbed far more than procedural knowledge. He learned to see like a shipwright, to assess timber with a glance, to feel when a curve was right, to hear in the sound of the axe striking wood whether the grain was aligned correctly. When the Viking Age ended, when Scandinavian societies converted to Christianity and integrated into European feudal structures, when warfare changed and raiding decreased, the demand for longships declined. Trading continued, but even there, other ship designs began to compete. The distinctive clinker-built warship became less central to Scandinavian culture. As demand decreased, fewer shipwrights trained apprentices. The knowledge began to fade, not immediately, not completely, but gradually, generation by generation. The sophisticated understanding that had built the greatest ships of the medieval world was lost. Clinker construction continued in modified forms, but the peak sophistication, the optimized designs, the accumulated refinements of centuries, those mostly vanished. By the high Middle Ages, shipbuilders in Scandinavia were building different vessels, cogs and other designs that reflected changed needs, and influences from other maritime cultures. These were fine ships, effective ships, but they weren't long ships. The era of the dragon ships had passed, and for centuries, the long ships themselves were forgotten. A few survived in ship burials, high-status Vikings interred with their vessels, sealed in anaerobic conditions under burial mounds. The wood survived, remarkably preserved. But no one knew they were there. The locations were lost, the stories forgotten. It wasn't until the 19th century that archaeologists began excavating ship burials, revealing the longships in all their sophisticated glory. The Gokstad ship, discovered in 1880, the Oseberg ship, discovered in 1904, Skuldelev ships, discovered in 1962. Each excavation revealed more about how these remarkable vessels were built, and as archaeologists studied them, as naval architects analyzed their lines, as experimental archaeologists built replicas and sailed them, the sophistication became undeniable. These weren't primitive. Boats built by people who barely understood what they were doing. These were cutting-edge vessels designed and built by master craftsmen who understood hydrodynamics, materials science, and structural engineering at a practical, empirical level that rivaled theoretical understanding developed centuries later. The modern replicas proved it. Full-size reproductions of the Gokstad ship, built using traditional techniques and materials, crossed the Atlantic successfully multiple times. They proved fast, seaworthy, and capable of everything the sagas had claimed. The longships weren't myths or exaggerations, they were real, and they really were as good as the stories said. This validation matters because it forces us to reconsider assumptions about medieval technology and the societies that created it. The Vikings weren't backward barbarians who stumbled into success. They were sophisticated, innovative, and capable of creating technology that remained unmatched for centuries. The longship represents what's possible when knowledge is carefully accumulated, preserved, and refined over generations. When craftsmen take pride in their work and understand that lives depend on their skill. When societies support long-term learning and don't demand instant results. When empirical observation and iterative improvement are valued over theoretical perfection. In our modern world of rapid technological change, of engineered obsolescence, of disposable products, the longship stands as a reminder of different values. These ships were built to last. They embodied knowledge that took centuries to develop. They were maintained, repaired, and treasured, serving generations of sailors before finally wearing out. And in the end, the story of how Vikings built their famous longships isn't just a story about boats. It's a story about knowledge, how it's created, how it's preserved, how it's transmitted, and how it can be lost. It's a story about craftsmanship, about the deep satisfaction of creating something excellent that serves its purpose perfectly. It's a story about community, about pooling resources, and efforts to create something no individual could make alone. The longships changed history. They enabled the Viking Age, allowing a relatively small population in a harsh land to reach across the medieval world. They carried raiders to England and France. They carried traders to Constantinople and Baghdad. They carried explorers to Iceland, Greenland, and North America. They carried colonists who would establish new societies in distant lands. None of that would have been possible without the shipwrights, without the men who walked through forests reading trees, who split oak trunks along the grain, who shaped planks with axes, who drilled rivet holes with precision, who lashed ribs with spruce roots, who stepped masts and bent sails, who understood in their hands and eyes and minds how to create vessels that could conquer seas. Their names are mostly lost. Unlike warriors who had their deeds recorded in sagas, shipwrights worked in obscurity. No poems celebrated them, no rune stones recorded their accomplishments. But their legacy endures in the ships they built, in the knowledge they preserved, and in the historical impact of the technology they mastered. When you see a Viking longship today, whether a preserved original in a museum or a replica floating on modern waters, you're seeing the physical embodiment of centuries of accumulated knowledge. Every curve, every joint, every detail represents understanding earned through experience, refined through iteration, perfected through obsessive dedication to craft. That's how Vikings built their famous longships, not through genius or magic, but through knowledge, skill, and stubborn determination to get every detail right. They built with their hands, but they designed with wisdom passed down through generations. And what they created was extraordinary ships that remain among humanity's great technological achievements, vessels that changed the world and still inspire wonder a millennium later.